number 3, which talks about stresses in beams. First, we shall discuss about what is meant as stress. So, stress in the model number 1, we have understood that it is a resisting force acting per unit area whenever force is acting. Hence, in the model number 1, we told that whenever a compressive force is acting on a body, the resisting forces created per unit area was called as compressive stress. The same way resisting the tensile force per unit area was called as tensile stress. The same way if a beam will resist the bending moment is called as bending stress. The same way we'll be talking if a shear force is resisted by per unit area, that is called as shear stress. So in this module we'll be trying to learn how to calculate the bending stress as well as shear stress. So today's session we'll talk about how do we calculate the bending stress acting on a beam. So hence first we shall talk about what is meant by an beam here. So beams are subjected to a bending moment and shearing force from section to section here and develop the stresses. Resisting the bending moment is called bending stress. Resisting the shear stress, shear force is called shear stress. Hence, whenever we talk about only bending, we don't talk about shear force. So such a beam is called as a simple bending theory, where stresses due to the bending only is considered here. So it's called a simple bending theory. That's what we'll be talking now with this regard. So coming to the what is meant by and pure bending. So let us consider a small beam here where I have a simply supported beam. There are A support and B support subjected to 2 points load. So hence the reaction will be W here at B and B because it is then symmetrical loaded. So hence when we draw an shear force diagram, as the force is W, it comes like this. Then come over here at this point a W force acting. So hence W minus of W is 0. And then from C to D there is no any forces. So hence it is 0. In the same point at point D we have a force acting downwards. So hence we have an minus W, and the same way coming over here, then at the point B we have opposite reaction for W, hence reaches here. So this is called as shear force diagram. The same way when we talk about the bending moment diagram at this point, so bending moment diagram is nothing but at this point we have W into 0 is equal to the force per distance 0 is 0. So hence with that picture we have written the bending moment at this point is equal to 0. Hence at point C here the force in per distance W into the distance is equal to A. So hence the moment is W into A. The similar way this beam will try to bend, making and sagging bending moment. Hence again force into per distance is nothing but W to A. I get a WA. And between these two forces I don't have any forces, so hence has a constant bending moment. So hence this portion from portion C to D where I don't have any shear force but I have the bending moment values, shear force 0. So this portion C to D is called as an pure bending case. Hence whenever the beam bends into arc of a circle, the bottom portion, case of simply is called beam, this extends and the top fiber will decrease. So hence the bottom fiber is subjected to a tension and top fiber is subject to a compression. But when you observe the middle layer, it is a neutral layer where there is no compression nor tension. So hence resisting this compressive force is called as compressive stress. Resisting this tensile force is called as an tensile stress. So hence a small diagram has been illustrated writing down the compressive stress in the top and the tensile stress at the bottom, and in the middle layer where you don't have any stress, that is called as a neutral stress, and that axis is called as an neutral axis. So hence we understood with respect to an beam that whenever there is a sagging bending moment here, in case of a simply supported beam, the fibers below the neutral axis get stretched and the fibers are under tension. The fibers under the neutral axis get compressed, above the neutral axis get compressed, so fibers are in compression. If by chance there is an hogging, it is a vice versa. So in between there is a fiber called as a layer which neither undergoes nor tension nor compression. This layer is called as a neutral layer, and the trace of this cross section is called as neutral axis. So hence with this we talk about, for doing the derivation we have to assume some criteria, that is, this is the bending behavior of a beam. So hence we always assume to do the derivation that beam is initially straight and each and every layer is free to expand or contract, and the material is homogeneous, isotropic, Young's model is constant and it obeys Hooke's law. Stresses are within the elastic limit, and the radius of curvature the beam is very large in comparison to the depth of the beam. A transverse section of the beam which is plane before bending will remain plane after bending, and the stresses is purely longitudinal. So for doing the derivation we assume this made in the pure bending theory. So hence we'll talk about now, and note that member is taken as homogeneous and it is same all over. That means to say the properties along x direction, y direction, x direction or all are same. That means to say it's called isotropic. So hence I'll consider a transverse section of the beam here. This is called as transverse section of a beam and I consider small elemental area dx. Hence when this small elemental area is considered, so I'll just take the next slide where I have taken an elemental area dx of that part of a beam, and this part of the beam, the top element is taken as AB, the middle neutral axis is taken EF, and another layer is taken here as GH, which is away from the neutral axis as a distance of y, and the bottom layer is CD. Hence the top layer AB is experience a compression and the bottom fiber is and tension. Now considering this beam section of length dx subjected to pure bending, after bending the AB is shortened in length whereas the fiber CD is increased in length. In between there is a fiber called as EF which is neither shortened in length nor increased in length. This is called as a neutral layer. This is called as EF. Let the radius of the fiber E dash F dash be R. Let us select one more fiber called as GH. GH, take distance of Y from the fiber EF as shown in the figure. Hence, in this problem, EF is equal to this distance EF from here to here is taken as dx. The similar way, E dash F dash, the neutral axis, there is no expansion, no contraction. Hence, EF is equal to E dash F dash. Hence, we consider dx. Now, a relationship between EF. So, if I take here tan del theta is equal to opposite side by adjacent side. Hence, opposite side is nothing but the length of dx by the adjacent side is r. So, hence, When we ignore the small deformation, we get a derivation is equal to EF is equal to E dash F is equal to dx is equal to R del theta here. So hence the initial length of GH is equal to R del theta. After bending the new length, GH equals to G dash H dash, that is equivalent to R plus Y, where the Y is taken here the distance from the neutral axis to the GHY into d theta. So hence we get an equation R del theta is equal to Y del theta in this problem. So hence now considering a strain in the length of the fiber, GH is equal to the change in length, that is now the length has changed from R del theta to Y del theta, and the original length of the member was R del theta. So hence the difference between these two will give a value of equivalent to Y del theta. So hence the strain is equal to change in length by original length. I get Y del theta by d theta. So d theta gets cancels off here, and hence I get strain is equal to the Y by R. And also we know that in the problem in the first module, we know that Young's model is equal to stress by strain, and strain is equal to stress of the bending divided by Young's modulus. It's been written here. So hence with that we are going to get here the equation, the bending stress by Young's modulus is equal to Y by R is equal to, so hence if I take the E here opposite, so hence bending stress is equal to E by R into Y. What is the first equation, the relationship, what I get. Then in the same way, now we will talk about the neutral axis. Neutral axis coincides with the horizontal central axis of the cross section. So hence with that regard, on one side of the neutral axis there is a compressive stress, on the other side there is a tensile stress. So this is an compressive stress and this is a tensile stress, and these stresses form a couple. That means the force act here, and the same way a force moment acts. So hence a couple moment is acting here. It means to say a force, compression force and tensile force. This forms a couple, and this also force distance forms a couple. The moment of this couple, which resists external bending moment, is called as moment of resistance. Hence with this, in the moment of resistance, we talk about, we consider small elemental area of del A. Hence the force of this elemental area is equal to stress into elemental area dA. And already we have done the derivation for stress is equal to E by R into Y into dA earlier from the equation 1. Hence doing this here in the equation, we get E by R is equal to E by R into Y square dA. So hence in the first semester we spoke that y square dA is called a second moment of an area, that is equivalent to the moment of inertia of an element, and from the first year basics of building structures 1. Hence substituting that equivalent to y square dA is equal to moment of inertia, we get an equation m is equal to E by R into I in A. So moment of inertia with respect to the neutral axis. So hence finally an equation m is equal to Young's modulus by radius of curvature into the moment of inertia. Finally we get the bending moment equation is equal to m by I is equal to E by R is equal to the bending stress by Y. This equation is called as Bernoulli equations. So as part of your syllabus, you have to remember the equation for numerical problems to be done. So here, where E is called Young's modulus, R is called as radius of curvature, which we have taken in the derivation, M is called a bending moment at section, I is called as moment of inertia about the neutral axis, and sigma p is called as the bending stress, and y was the distance of fiber from the neutral axis. So hence with this we are going to calculate here z is equal to, again continuing the equation, z is equal to I by y, that is called as and section modulus. So hence we get an equation moment of resistance is equal to stress into section modulus, where the section modulus equivalent to I by y max of the member. So hence the moment of inertia as per the first semester knowledge, I is called as BDQ by 12 for a rectangle section. So hence the unit was mm to the power of 4 and y is equal to mm. So hence the unit of section modulus will be mm cube or meter cube. So now we'll go into the numerical problems for standard sections. For example, I go with an rectangular section. For rectangle section having a breadth and a depth d in this problem. So hence in the first semester we know that moment of inertia of a rectangle section was equivalent to BDQ by 12, and y max in this problem is d by 2 d by 2, that has been substituted. So hence you have to remember in the examination when the section modulus of rectangle cross section is given, the formula is BD squared by 6. The similar way we'll be doing for an hollow rectangular sections, where for hollow rectangle section this is a cutout portion, that is this is a cutout portion here. So hence the moment of inertia will get reduced. So hence it is written as BDQ by 12 minus of inner breadth and DQ by 12, and y max is however capital D by 2. So hence the equation is written for an hollow rectangle section like this. In the similar way, we have the next kind of section called as circular section. So in the first semester building structures, we understood that moment of inertia of circular section is pi d4 by 64, and the distance of y max is d by 2. So hence the formula to remember as the section modulus of an circular section is pi d cubed by 32 to be remembered in the problem. So hence with this we'll go with an triangular section. So in the first semester we knew that the moment of inertia of an triangular section was equal to bh cubed by 36, and the central distance in the building structure 1 we proved that it is h by 3 and 2h by 3. So hence y max in this problem is 2h by 3, that will be substituted. So hence the formula to remember the examination, that is the section modulus for triangle section is bh squared by 24. So hence these are the formulas to remember the examinations. Now we'll go into an numerical problem. So here we have a problem of a simple support beam, where the beam is having a span of 5 meters and the bending stress taken 50 MPa, and the factor of safety is given as 5. Hence what is the maximum UDL we are supposed to calculate a load in this problem? Already the bending stress is given. So hence as the maximum stress is given, safe stress is equal to the maximum stress divided by partial safety factor. So that has been here used in the problem. Hence the permissible stress by partial safety factor 5 is equal to 10 Newton per mm square. So hence with this regard we are going to get the equation m by I is equal to stress by y. In the same way we get m max. With that we have the equation here in this problem. So hence we consider, and we know that for a simple support beam is from the second module, that is WL square by 8. So hence that is substituted here and is equal to the m by I. The equation is used, what we did the derivation, m by I is equal to the E by R into the bending stress by y. So hence The moment of inertia is calculated by simple formula BdQ by 2 for rectangle section, and Y max we know that nothing but d by 2. So hence bending moment from the second module, you know that is W L square by 8 that is being calculated, and finally based on the equation substitution you get the permissible load as 9.6 kilonewton per meter. So such kind of problems can be asked for 10 marks in your final examination of VTU. The same way we have a second problem here, where this problem is subjected to an UDL as well as an point load, and the point load is acting at a distance of 2.5 meter, and other way is 3.5 meter, and a small rectangular section is being given where the depth is given as 50 mm here, and the bending stress is already given as 8 Newton per square. So hence the job is in this problem to find out the maximum compressive stress as well as tensile stress in this problem. So hence the first step is to calculate the reactions. So keep your finger at MA is equal to 0, and first talk about the UDL, that is 12 into 6, which is making an clockwise movement, and the perpendicular distance is 3 plus 9 into the perpendicular distance is 2.5, and VB is making an anti-clockwise movement, hence it will be minus. So hence the workbook here, what I told just now has been told here, and find the VB value. Then we get VA is equal to 41.25. This was understood in the second semester when we talked about shape force diagram, bending moment diagram. In a similar way, in the first semester of model number 1 we have discussed. So hence with that we draw the shape force diagram the same way how we understood in model number 2 of the shape force and bending. So hence I have a RA 41.25, then come over here UDL, so uniformly varying 41.25 minus of 12 into 2.5 comes up to 11.25. 11.25 minus 9 is 2.25. Then again you have UDL, so 2.25 minus of 12 into 3.5, I get 39.75, and then 39.75 plus 39.75 is equal to 0. So this is called as an shear force diagram. So with this we calculate the bending moment calculations the similar way how we understood in the model number 2 is being calculated. So after this we know a formula M by I is equal to sigma by Y. So substitute the bending moment, the maximum bending moment, by moment of inertia BdQ by 12 is equal to stress by Y. So hence you will be getting the value of B in this problem, and in the solution is given as D is equal to 2 times of B. So this is 462.22 Nm. So in the similar way I have another problem where an rolled steel joist of 200 mm into 450 mm 4 meter span simply support ends, and it is having the two flanges, top is 300 by 200, and one more plate is added to that. Such a beam is called as a built-up beam, and the span is about 4 meters and is given in the maximum stress not to exceed 120 megapascal. Megapascal is nothing but Newton per mm square. So in the second semester we spoke about how to calculate moment of inertia. A similar workbook has been done here. Please go through this. If you have any doubts you can call me on my mobile. In the same way we go into the moment of inertia calculation. M by I, after calculation moment of inertia, sigma by Y. So hence we get P is equal to 4.95. Then we substitute that in similar way, and if it's a point load we calculate is equal to 247.35 kilonewton per meter. So hence this is a problem with here. In the similar way we have another problem with an T section. So please go through that problem if it is a T section, and there are some practice problems here. And also have put some theory material notes. Please download that from the Edmode platform and try to understand the concept. If you're not able to understand, please call me by. So have a good day. Have a safe.